In second week of our course, what I was saying is two new methods have been, uh, two new concepts have been introduced. Like in the second week is a flow through the rectangular duct, sorry, triangular duct. Here, how the flow inside a triangular duct can be discretized and solved. The concepts, both the concept discretization as well as the how the governing equations can be reduced. These two methods have been uh, introduced. Okay, so let's start with the questions. Uh, again, from actually these sections are meant to be interactive. So from this section onwards, I will be displaying the questions. I will give some time for you to think and uh, just put your answers in the comment box. Then I will explain so that you can everyone can catch up with it. So our first question is uh, in the figure a triangular duct is shown. So what will be the with uh, what will be the governing equation for a steady laminar flow through the triangular duct shown in the figure? So here,
A.
excuse me,
Option number A, right?
please put your answers in
Okay.
the comment box. I will give. Everybody starts giving answers, then it will be really difficult for us. Okay. So I will give you time. Please put in the chat box. So the uh, question is, what will be the governing equations for a steady laminar flow? So the key takeaway, the key points in the question is that first thing is the given coordinate system. So here you have to check what is the coordinate system. So this z, y, and the flow is happening in x direction. So the cross section of the that is a triangular cross section is in on zy plane. So that is the main takeaway from this question. So please put your answers in the comment box. So I got answers A, D. Okay, so let's check first answer. So here the flow is happening in uh, x direction. So this is the governing equation. So in this side, these terms will go. These terms for a steady flow, this term will become zero, and again, which terms will uh, happen. So reducing the terms, the here the velocity is only the function of uh, y and z. So dou u by dou z becomes zero. This term becomes zero. Then again, this v and w velocities doesn't exist. So these all entire term becomes zero. Again, if we neglect the this term, we have left with entirely this one. So here again, what we are left with is the flow is happening in x direction. So the Pressure gradient, what will the driving force or the pressure gradient will be dou P by dou X. And again here this, since the flow is happening in flow is changing is uh, when the flow is fully developed, it won't be having an actual variation. It will be having a what variation inside this cross section. So this u is velocity u by x won't exist. So what we are essentially left with is dou square u by dou y square plus dou square u by dou z square is equal to uh, dou p by dou x. So our answer becomes this one, option number C. Okay. So most of you have answered D. Okay. So the issue with uh, option number D is here it is shown like it is written as dou square u by dou x square. This time dou u by dou x, because there won't be any variation of u along the x. That is, the flow is happening in this direction, x direction. So actually, for a fully developed flow, in last introduction session also we have discussed. In a fully developed flow, the velocity won't be varying in axial direction. That is, along the tube, it will be varying along the cross section. For a, if you remember, for a tube, round tube, for a fully developed flow, it is of a parabolic cross section. So it will be like that. So meaning that it is only varying radially. It is not varying axially. So there won't be any axial variation in the flow that's happening inside the round tube, because I am using this taking round tube because it's a well discussed problem, well known problem. So you know, everybody will be knowing the profile of velocity inside a round tube is parabolic, and that means the velocity is only vary radially with respect to radius only. It is having, so likewise here also it is only varying in the cross section, that is in zy plane. So the y and z components will only exist. This dou u by dou x at both sides. Dou u by dou x at the LHS, as well as dou square u by dou x square in the RHS becomes 0. So that's why the option is option C. I hope it's clear for everyone. So moving on to next question. So it's a variant of our first question only. For a steady, fully developed flow through a duct, shown in the figure represents a balance between which of the following terms? Inertial, the options are inertial forces, viscous forces, and pressure forces. So before going to the thing, so you can start answering. So what will be the options? I mean answers for the here. Option number A gives 1 and 2, that is inertial and viscous forces. Option B is 2 and 3, that is viscous force and pressure forces. Then option C is 1 and 3, that is inertial forces and pressure forces. Then third one, 1, 2 and 3, all of them. So what will be the option? Anybody? I've got one option B. So everyone else is agreeing with that. Can we move forward? So let me ask you on other terms. What are these terms? So these are the governing equation. This one is the governing equation for the duct. Suppose I am taking these, dividing it into 4. Suppose this, as I am taking it A, This time I am taking as B, this time C, and this time D, this large vector. So what's the uh, a name? What do you call these terms? The first one, what is A called, B called, C and D? What will you call these terms? So which one of these is the inertial force? So somebody has answered C. So can you answer, I mean, reply which one is inertial terms, which one is our viscous force? So the three options in our uh, three forces given are inertial, viscous, and pressure force. So first, if first one is inertial force, which one is the viscous force? So here, I will answer for that. So this one, this term, it's called the inertial force, and this one you will be understanding because since P is present there, it is called the pressure force. Then, so next one, this term that is called body forces. Because the forces that is acting on a floor or on a system due to the virtue of any external field, that's called body force actually. If it is like a gravitational field, electromagnetic field, all such forces will be taken considered as body forces. So the last step, that again is evident because since the mu is present here, it is the viscous force. So for a fully developed flow, which what is which forces uh, creates the balance. So we have uh, derived the equation, the governing equation for this particular flow. There we what eliminated this term. This becomes zero. Again, this we neglect. Also, this term goes zero. So what we are left with the pressure forces. That is the third one, and this term that is the viscous force. That sorry, this one is the second, and this is the third. So our option becomes 2 and 3. That is option B becomes answer. Well, the balance is created between viscous force and pressure forces. Hope everybody got it. So moving forward to the next question. So here we have an elliptical duct. So the question is, what will be the vector form of the governing equation for the flow through the ellipsoidal duct shown in figure 2? So here the catchphrases in the equation or the terms you should notice in the question is that first one is vector form, second one is ellipsoidal duct, and if it is even if it's not given, the coordinate system is explicitly shown. It is evidently shown, so you will have to notice the coordinate system and also the form of the governing equation. So the formulation will be same as that of the first one. So what will be the answer? So you can put your comments, answers as comment. I'll give 1 minute or 2 minutes. So I will repeat. So we want the vector form of the governing equation through an ellipsoidal duct. So one answer is C. Please don't be shy in answering. So it's only for your better. You will remember if you even if you use an answer, if it's wrong, then it will be better, easy for you to remember it. Actually, so one person has answered C. Please answer others also. Okay, D or another person is given D. Okay, so actually, it's simple. With the first this uh, term itself, we can find out because it's asking vector form. So vector form means this only this equation is having vector form on both sides because it is both written in del terms. So mu del square u is equal to minus del p. So this is both side of the equation is having it's written in vector form. So this one, this is an easy, but the confusing thing is when you are taking this one, if you are concentrating on this particular coordinate system, then here the flow is happening in z direction. So, like as if you are uh, considering like if you are thinking like the previous question, you won't be finding any answer here. Sorry, you will be going with this option here because here u is given, here v is given, here w is given. So if you are thinking, okay, the flow should happen in set direction, so the uh, time should be in w, that is the z component of velocity. Then again, it's wrong because when we are using the del term, we won't be using the component. We will be taking as a vector itself. So here it's explicitly written as u is the velocity vector. That is u is ui plus vj plus wk. So that here it's written u is the velocity vector. So the only uh, suitable answer is option D.
So,
Excuse me.
so I have a doubt.
Yes.
Uh, that can you please go on to the last slide?
Yes.
Yeah, this in the lecture, sir had started with this particular equation on option number D, and then he had used that Gaussian to convert this into the option given in into the equation given in the option number C. So, is this to make the scalar on either side of the equation? Means that's why we use that Gauss displace. I mean, I just forgot the name.
Actually,
A Gauss divergence
Gauss
theorem.
divergence theorem.
Yeah,
Actually,
yeah,
Gauss divergence
yeah. So
theorem is we are simplifying. Actually, from we are
means
dimensionally. Yes.
to make it a scalar on either side of the equation, from the vector form to the scalar form.
No, actually, yeah. One side it will make the one side of the equation to scalar form because the other term, the other side have the vector because we are actually
No, the
reducing.
thing on the left hand side is also a scalar, no? It's a dot product between two vectors. That is a scalar, right?
Yes, yes. So divergence theorem,
So
all this actually we are reducing from this three dimension to two dimension and two dimension to one dimension. These are the theorems what we are using. So here
okay,
the
okay,
entire vector form it's a volume term. For the three dimensional form, from the three dimensional form, we are taking the two dimensional form. That's why the Gauss divergence theorem
okay,
have been taken. So that we can use an aerial area integral. If not, we have to go
okay,
for a
okay.
volume integral. Then we have to eliminate the volume terms.
Yeah,
So we
oh,
uh, for the ease of calculation, we will reduce it into volume integral to area integral using divergence
okay,
theorem.
okay. Yeah.
Right.
Thank you, sir.
So the other question, next question is, which method would you use to solve for the velocity field in an ellipsoidal duct if you wish to solve in XY coordinate system? So here the three most common methods of CFD uh, has been written here. This one is finite volume method, another is finite difference, and finite element. So the question is, which would you use to solve in a XY coordinate system? That for a uh, ellipsoidal duct. So anyways, this option is shown here. That is T. That is finite, either finite volume or finite uh, element method. So can anyone say why is that? Why we won't go for finite difference method?
Because finite difference method is the method where it is used where lines are parallel to the x and the y axis. So it's used only for the rectangular ducts or for a uniform shape type of thing. But for any general shape, finite difference method can be used because it discretizes the element into the triangulated facets. So that makes it general for any curvature to be used.
Actually, there is one small difference. It's like a finite difference method. Actually, here it's asked for XY coordinate system. Actually, the best method to solve for CFD in an XY coordinate system is finite difference method. But the catch or the change is for an ellipsoidal duct. For ellipsoidal duct, so it's like so this is our ellipsoidal duct. So here, if you are meshing it into uh, Cartesian elements, like I am meshing it into a square or rectangle cells, then what happens is like towards the boundary, it will make uh, the elements won't be straight. Even if I mean, I can't create square cells at the boundaries because the boundary is having an oval shape, or for any, for that matter, for any irregular boundaries. Uh, so if I have to use finite difference method here, if you are asking if I can use finite difference method here, yes, I can use finite difference method here. But the issue is I will have to uh, refine the mesh. That is to reduce the cell size. That is the volume cell size to such a small extent that this circumference, I can divide into almost fit into squares. So that much refinement I will have to give. Or another method is called a hybrid meshing. I will have to give some other layers here, bound some layers of some uh, layers should I should give some other layers with some gradually increasing growth factor, the mean stretch factor. This, but these two are meshing. That two process will make the first one. That is, if I am going to refine the given area to a very high refinement, then the number of cells will be very much higher, and that will make the computational process uh, lengthier and costly. The second one will, if I am to give this boundary layers, I mean boundary layers of mesh, or this wall layers of mesh here, then that will make the meshing process difficult. So the methods are finite volume method and finite element method. I hope that's clear.
In finite volume method also we'll have the same problem. There also geometry is irregular. So we'll not face the same problem there.
Finite volume method, actually we are taking centroids actually. So finite volume method, uh, uh, Actually, this finite volume method, we can go for unstructured grid. So in the question, if you have watched the videos, that video 7 explains it, I think. Why we are taking, because we have a unstructured, I mean, complex geometry or difficult shape geometry boundaries. Then we can go for triangular elements or I mean, some other kind type of elements. So the mesh won't be uh, structured. The mesh become unstructured, and unstructured grid is difficult to solve in finite difference method, and it's not it won't work well with different methods, let's say.
Can you explain this finite element method also, how it will be helpful? This also will be
Fine,
useful.
a finite element method, we are creating as elements. Uh, what we are taking is in finite difference. Suppose one cell, if you are taking one cell, so we are taking this difference, cell differences. So what we are uh, between what happens inside or one, if we are taking this one particular, I mean one wall to different wall, one to next wall, what is happening. So in finite volume method, suppose these are two adjacent cells, we are taking this conservation loss. So what is crossing the boundary of the cell? So here we are concerned with the elements, I mean nodes. Here we are concerned with the volumes. Then finite elements, we will be concerned with the points. In each of the points, we will be solving the equations. These nodal points. That's the difference. And the uh, solution method is a little different than what we are doing in finite volume method and finite difference method. And finite element method takes much more computational effort, let's say, compared to finite volume and finite difference. That I think in the coming week videos, you will sir will be explaining.
Okay, okay, thank you.
So here, uh, next question: which discretization method is known for its strict conservation property and making it ideal for fluid flow problems? So again, our three things: finite difference method, finite element method, and finite volume method. So here, if you have watched the videos, you have seen what we are taking the starting with the vector equation, then we are using uh, what converting it using divergence equation, then we are taking the integral form. So that's what we're making. So any finite volume method can only be uh, done through the integrating of this our governing equation. So integration is the conservation itself. So what we will be doing, we will be taking, we will be applying this conservation property to one particular cell, or that we will be finding the discretization equation or the governing equation for a cell, and we will be integrating for the volume. So the as a property or as a characteristics of the method, finite volume has conservation is inherently conservative. So if you have followed this uh, conservation of mass or conservation of volume methods in thermodynamics or any such subjects, you will know what's a control volume. So like that, what then if we are assuming a control volume, then we are only uh, concerned with what crosses the boundaries. So what is the influx and what is the flux. So whatever it is, the difference between the inlet and outlet flows gives the uh, is what is left inside the volume. So by that, it gives a conservation property. So it is inherently built to that scheme, I mean method. So moving on to next question. What is the main advantage of forward difference schemes compared forward and backward difference schemes compared to the central difference scheme. First one, higher accuracy at all derivative approximation, simpler implementation of on non-uniform grids, then better stability for certain types of equation, then ability to handle complex boundary conditions. So please give your answers in the comment. Got one answer C. Anyone else? Okay, let's see how what's the difference between forward, backward, and central difference schemes. So these schemes, I mean forward scheme, backward scheme, and central difference scheme, everything is we are deriving from the Taylor series equation. Last time also we had some confusion on this. So uh, this one, first equation is Taylor's series for a continuously differentiable function at x is equal to xi. So if I am taking, suppose just assume one linear element. So with cells points as I plus 1 and I minus 1. So if I am moving forward from this point, or we are reaching this point, then the x becomes x is equal to x plus, sorry, x is equal to x at I plus 1. So I plus 1. Then substituting in the this equation, it becomes f of I plus 1 or f of xi plus 1 becomes, we are substituting all the x's with the xi plus 1. Then the equation becomes this, where this h is the higher order terms. We are not expanding beyond this part. So this h represents the higher order terms. Again, if I am substituting this x, I am substituting x of I minus 1 for x, then the equation becomes f of x minus 1, f of x I minus 1 is equal to, substituting for all the x's with x I minus 1, then f of xi plus xi minus 1 minus x of I at dou f by dou x at I plus x of I minus 1 minus xi the whole square by 2 factorial plus a second order term dou square f by dou x square at I plus h. Again, this is the higher order terms. So from equation number, from this equation, if I am to take this dou f by dou x, the first order term, first order differential out, then the equation becomes f of I plus 1 minus f of I. So this is taken to that side. So f of I plus 1 minus f of I by x I plus 1 minus xi minus xi plus 1 minus xi by 2 dou square f by dou x square plus h. So this we can write as this we can reduce this I plus x of I plus 1 minus xi. I am writing it as delta xi. So the equation becomes dou f by dou x at I is equal to f of I plus 1 minus f of I by delta xi plus the terms in order of x delta xi. So the term order that we are neglecting. So we are if we are only uh, looking for first order derivative, that is dou f by dou x, then the order to which order we will be truncating or eliminating will be the order of delta x, because here you can see this term is delta x. So we are truncating this term here. So the truncation error will be in the order of delta x. So here you can see this uh, f of I plus 1 and I are needed, then delta x. So the properties at 2 points are needed. Then again the same approach is applied on the second equation, that is toward backwards. If I minus 1 point, then the equation becomes like this. So this equation is called forward differencing scheme, FDS. This one is backward differencing scheme because we are going backward. So these two are the forward differencing and backward differencing. If I am combining these two, if I am adding up these two, then that becomes this one. This is essentially the central difference scheme. If I am taking these two equations and I am adding these two equations, I am taking these two equations, then adding it up, resolving, then it will become something like that. Here, if you see in the denominator, it is delta, x I plus 1 minus x I minus 1. So it is del x I plus 1 minus x, also x x of I minus x I minus 1. So the combination of these two terms. That's why it becomes 2 delta x. And also in the numerator, if you see, the uh, terms are f of I plus 1 and f of I minus 1. So the question was, what is the main advantage of backward and forward schemes compared to the uh, central difference scheme? So here the best advantages is uh, application on non-uniform grids. So again, if you look in these equations, you can see here the terms. When we are establishing an equation in the uh, ith column or one particular point, we only need either the point ahead of it or the point behind it. So we only need the information from one side. But if you see in the central difference equation, we need the information from backward, I mean behind and forward. From both sides, we need the information. So we know how we solve the equations. So we will be like most of the uh, methods will be like sweeping from one point to another. So when we are sweeping from one corner to another, we won't be having the information at both sides of the one cell. So either we will have to put a dummy value to the cell ahead of it or behind it. Then we will have to iterate and then get a logical answer there. And again, one another disadvantage for central difference scheme is that we don't have any information on f of I in this scheme. That is, we are taking dou f by dou x at ith cell, but it doesn't have any, the f of I doesn't have any role there. So that's again a disadvantage. So uh, when we are taking some non-uniform grids, suppose if it is a uniform grid like this one, it won't be a suppose these are the centroids. Then I can suppose boundaries values is a heat transfer problem. Suppose this is a 100 degrees in one, 0 degrees in one side and 100 degrees in one other side. Then suppose we can just assume some values here. We can logically split this difference 0 to 100 and put assume the values, so that when we are applying the central difference equation here, then we will be having some estimate beforehand for the I plus I minus 1 and I plus 1 cells. But when we are going for some I'm not right, some non-uniform grids, then these kind of logical uh, estimation on the both sides of a given cell will be difficult. So in those cases, the solution time will be, because to reach some logical distribution of the parameter over the domain will itself take some time. So uh, all such terms, all such discretization methods where we use non-uniform grids or non-uniform step size, there we will be taking forward or backward skips. Hope that clears it. Next one, what's the primary factor to consider when choosing meshing strategy for a particular CFD problem? Please give your answers. So, one answer is B. Okay, C. Okay, you can see. Okay, so let's see what it will be. So the options are cost of meshing software, user experience with the meshing tool, balance between accuracy, computational cost, and meshing effort, availability of predefined mesh templates. So if you are working in an industry or something, this won't matter much actually. When we are going for uh, some research or new problems, or where we uh, have to find the accuracy or best uh, mesh or something, then these parameters come into existence. So the answer is C, because we have to need to strike a balance between accuracy, computational cost, meshing effort. Like I have explained earlier, the uh, much more refined the meshes, the accuracy will be more. But beyond a point, the accuracy won't be varying much with the refinement. So accuracy is accuracy and computational cost. These two we will be uh, optimizing with something called mesh sensitivity studies or grid independency studies or something. So that we will be suppose we are taking a mesh with n elements, then we will be next step of element will be n and 8n. So we will be the rule of thumb, it says like we have to go for the 8 times larger. So if we are keep on going to increase like this, the even the grid independence study or the mesh independence study, mesh sensitivity study will take a lot computational cost. So what we will be doing is we will be striking a balance between accuracy and computational cost. And the third one, meshing effort. This come into picture when we are meshing complex geometry or we are meshing different geometries time to time. Suppose like if we are meshing similar kind of geometries, some exhaust manifold or something. So all those things will be having similar shapes or sizes. So even if we are continuously doing it for different types with small variations, we don't have to find this mesh different mesh sizes or mesh parameters. If I say so, mesh parameter finding mesh parameters, we don't have to put much effort in meshing or finding mesh parameters uh, if you are repeating similar kind of geometries. But if you are doing entirely different geometries from time to time, then this meshing effort comes into picture. So most of the people will be thinking of these two, accuracy and computational cost. But again, this meshing effort is inherently there. Most of the time, it is left out because people think of in industries what they will be doing. They will be meshing similar kind of geometries again and again. So they will be having some predefined templates or predefined values there. They will be having some, okay, this number of the minimum element size should be this much to capture the variation of the quantity I am measuring or I am studying. So this meshing effort won't be much there because all the mesh parameters, some angles, some maximum element size, minimum element size, all those things will be defined there. So there they only need if they only have to strike a balance between accuracy and computational cost. I hope that clears it. So next question is which of the following factors primarily influence the accuracy of a CFD simulation result? Options are geometry complexity, mesh type, mesh density, software used for meshing. So here, uh, if we say all these uh, four things, geometry complexity, mesh type, mesh density, software use, everything influences the CFD result, but most importantly the mesh density. That is the uh, refinement actually. Mesh density means if we are taking some particular volume, then how much cells are there. If I am taking some unit volume of my entire domain, then what is the number of elements or what's the number of volumes or cells in that given volume? So that's the density. I mean mesh density. Mesh density is actually directly proportional to the refinement. So in all these three, density comes first, then geometric complexity because mesh density is directly proportional to this geometric complexity because if the geometry is having some particular bends, turns, twist or something, we are forced to implement finer meshes there. Or like I said, we have to create some prism layers or boundary layers to capture the uh, changes as such. So moving on to next problem. When comparing structured and unstructured mesh with the same number of elements for a simple geometry, which one is likely to have better solution accuracy? Options are structured mesh, unstructured mesh, both will be having same accuracy, then depends on specific problem. So option is A. So here, what things in the question, because all these things depends on the question. Here, the question is when comparing structural and unstructured mesh with same number of elements, these two can be confusing. I mean, it can divert the answer if we are not reading it together with the simple geometry. For this thing is the structured mesh is only good when the geometry is simple. So, with same number of cells is only applicable for simple geometries. Okay, moving on to the next problem. How are boundary conditions implemented in CFD methods? They are applied directly at grid points, that is finite difference method, or element nodes in a finite element method, or next one, source terms are incorporated into discretized equations. C, both A and B depending on specific boundary conditions. Then fourth one is D. It depends on the specific solver algorithm used. So please give your answers. I think the course not uh, we have seen some boundary conditions in the first week and second week. So how are we giving boundary conditions? We are applying boundary conditions uh, in a CFD method. Okay, uh, it is applied to here itself. It is directly applied to grid points or element nodes. So both finite difference method and finite element method. So nothing has been told about finite volume method here. So again, source terms are incorporated into discretized equation. So I hope you know what source terms. If not, source terms are the terms in the equations which is the driving potential, which is a driving term. So in our equation, um, we move back. Uh, so here, if you see, so this is the driving potential. That is the pressure gradient becomes the driving potential. This is the source term actually. So in where temperature variation, if we are solving a temperature distribution over a flat plate or something, there the source time becomes the temperature generation. So such times which mainly contains the driving force, driving terms is called the source terms. So actually the answer is C. We can use both uh, boundary condition, depends on the problem. Actually depends on actually I think in the last session, yeah, I have discussed that what is Dirichlet conditions and what is Newman conditions. So suppose we are giving a particular value, suppose this is a rectangular grid or something. So I am taking here in this particular boundary, this side of the grid, I am taking as temperature as 0 degrees Celsius. Here the temperature I am taking as 100 degrees Celsius. So here I am giving the direct values, whatever the nodes, elements, anything here. I am assigning the values. I am assigning some particular values, constant values to that elements or nodes. So such kind of boundary conditions are known as Dirichlet boundary condition. If suppose um, in this end it is not zero, but here this end I have been insulated. This particular end been insulated. So meaning what, I can't give any temperature there because I don't know this side I have insulated with something. So this side is completely insulated. So I can't give a particular value of temperature there. So in such condition, the boundary condition here becomes dou T by dou X is equal to 0. That is, the temperature gradient won't exist because temperature gradient means with respect to X, what temperature. So if we are taking this as X direction, uh, temperature gradient means what? How the temperature will vary according to X. But when it's an insulated condition, at that point, it won't be varying with the X because it is insulated. So such a point, the boundary condition will be giving us uh, some equations. So these first order equations or something, or gradients equation or such things will be giving us the boundary condition. So this boundary condition cannot be taken as a constant value. Suppose we are dividing the if we are taking the algebraic equation, that algebraic equation need a constant value to suppose these are three cells I plus one, I minus one. Suppose I need constant values uh, at this point. If even if these 2 points are unknown, I can work with that. But one point, whatever points I am getting, I'll need some constant values. Then only I can solve for the others. So this term as such, I cannot apply here. So I will have to discretize this thing, and then I have to plug it whatever is left in this equation. After discretization, I have to plug it in the source term. So this that particular side of the geometry will be having some other constants plus some other terms of this equation will be going to the source term. So such boundary condition. So simply boundary condition that is not as a constant values, rather a gradient or differential equation. Such kind of boundary conditions are called a Newman boundary condition. So this Newman boundary condition we have to discretize it, and we have to take some terms of uh, sometimes after the discretization and plug that into the source term. So our answer becomes C, that we can give both constant values as well as the discretized equation. So first type is called Dirichlet condition, second one is called the Newman condition. There are more boundary conditions like Robin and all, and as the course advances, we will be studying that. So, and our next question is, which of these best define Dirichlet boundary conditions of a property phi at a point B in a boundary? Can you answer? D. Yeah, here as I have explained the last question, but all other thing is some equations, gradients, or first order, second order, third order equation. So all these things are not Dirichlet. So Dirichlet meaning, but I'll have to assign some particular constant value, some non-value I have to give. So only phi of B is a constant value in this. So the answer becomes D. So Our next question: what is the main disadvantages of FDM and FVM? Sorry, what is the main disadvantages of finite difference method over the other two? That is finite volume method and finite element method. Can you answer? Sorry. Please mute your mic if you are not asking any doubt or something. Sorry, I have to mute you.
Is this A?
Let me explain. Okay. Here, first one, finite difference method. So here, the first one we have already discussed. The second one we have already discussed. Because less flexibility for complex geometries, because in two of the previous questions we had explained that uh, finite difference method work well with simple geometries. So B is there, and also C, that is difficulty handling unstructured meshes. These two we have already explained in last questions. So these two are there. So the only solution left is with all of the above. Since fi- uh, we are using structured grid, sometimes we will have to go for higher number of refinement or something. So in such cases, if we are using our FDM or complex geometries, the computational cost will be exponentially high. So the answer is D, all of the above. So our next question is the ratio between the longest and the shortest side of a mesh. Hmm, so what's the parameter what's the mesh parameter uh, that is defined by the ratio of longest side by shortest side? Options are mesh orthogonality, mesh skewness, mesh aspect ratio, mesh smoothness. So it's like we already discussed about how meshing is done or what kinds of mesh are there. So suppose how do we know that uh, we have made some one particular mesh and that we can use that for our purpose. Uh, there should be some quality criteria. Quality criteria should be there. That should be met actually. Uh, if not, it's the our CFD simulations is only uh, good as our mesh. So we have to uh, first we have to set some check for some quality parameters. If the check, I mean, if the mesh satisfies the quality parameters, then only we should uh, we should move to the CFD simulations, because then only we will get physically significant results. So these four uh, uh, these four quantities are some of the mesh quality parameters actually. So here the question is which of those parameter is defined by the ratio between the longest side and shortest side. So from the question itself, we can get that this is a ratio. So here we have a ratio. So from itself, we can guess it is a ratio. Also, the aspect by we know we can uh, by the word aspect itself, we can think like I mean assume that it is something related to its shape. So let's see. Actually the answer is mesh aspect ratio. So let us see what are the other quantities or is these what are these quantities. So first of all, we can discuss about uh, aspect ratio. So in simple layman terms, we can say this the ratio between longest and the shortest side. So here, for example, we have shown one particular 2D grid where a stack of rectangle cells are there. So this delta y is the height and delta x is the length. So the delta x by delta y will become the aspect ratio. So these kinds of mesh, uh, this aspect ratio should be in some particular range for getting um, reasonable results. Most probably, we will be taking aspect ratio around 5, so that the longest side should be uh, around 5 times the shortest side. That is what the best criteria we will be following, but it depends on case to case. But actually, we can work with higher aspect ratios if it is a one-dimensional flow or something. It's an axially developed flow, like we have a flow in a uh, round tube and it is a fully developed flow. So in that region, if we are using some cells that are having higher aspect ratios, right? That region, if we are separately meshing with high aspect ratio, even then the results won't matter. I mean, results won't be affected much because there is not much variation in the axial region. So in such axially developed flows or fully developed one-dimensional flows, in such cases, we can go for higher aspect ratios. So this is in case of 2D mesh, the first picture. If it is a 2D mesh itself, we know there are different types of elements. So there are triangular elements, tetrahedral elements. When it becomes for three-dimensional tetrahedral elements, for triangular elements and such, we will be taking the aspect ratio in this manner. So it's a ratio of inscribed radius by circumradius. So in this uh, criteria, we will be considering for triangular elements. Also, when it's for a quadrilateral element, we when the mesh is unstructured mesh, or we can't expect all the elements to be uh, squares or rectangles. In such cases, what happens is that the diagonals, the ratio of minimum diagonals by maximum diagonals, that ratio will be taken as aspect ratio. That's for quadrilateral cells. Then hexahedral type. The hexahedral type element is like a brick-shaped, rectangular prism-shaped thing. There, the aspect ratio is taken as this maximum of the side lengths by minimum of side lengths. But more of a thing for CFD calculations, most of the word matrices we will be following is this one. Uh, because for CF, I mean, control volume, finite volume method, we will be mostly concerned with, we will be discretizing with respect to cell centroids. So, in such cases, in such situations, what we will be interested is these length, that is the distance between cell centroid and face centroid also, and uh, the distance between centroid and a node, or the corner, node or corner. So if A is the distance between centroid and a node, and because this type of formulation is needed to find when we are discretizing, the nodal values are also important. And here this phase centroid is important because in control volume technique we will be considering the outflux through the phases. So the unit outward normals as well as the phases, phase centroid, all such things will become important. So for a 3D element, most usually what 3D structured elements, the aspect ratio is taken as these two values A by B, where the distance between cell centroid and node divided by the distance between cell centroid and phase centroid. So that's it, aspect ratio. Aspect ratio is most commonly used with 5 or the best uh, standards is thumb rule is 5 actually. Moving on to next one. Similar one is skewness. Actually, skewness uh, is a one of the quality of quality measure for a mesh, where we will be comparing our elements to the regular elements, regular geometry. So suppose we are discretizing, we intend to discretize our domain with uh, triangular elements, then the regular or equilateral triangle will become the standard. So how much our each of our cells deviates from our equilateral triangle, that's the value of skewness. So here if you see, this is a equilateral triangle and this one is a skewed triangle. So the sides, the length of sides, so here the all the sides will be having same value, but here it kind of different. So this ratio comes into picture, how much this values differs. So here it's one equilateral chord or quadrilateral element is uh, rectangular quadrilateral element, equilateral element is shown, and this is skewed one. So with respect to size, we can define skewness with respect to regular equilaterals or equiangulars. So in both of these ways, we can define the degree of skewness. I mean, the value of skewness we can find out. So this here is I have shown like how the change in uh, cell side length varies, but calculating the length of sides will be difficult, or that will be another computational task when we are doing the meshing and all. I mean, unstructured mesh or this completely complex geometry, irregular geometries and all. So such cases, anyways, we will be finding with we need angles and normals. You might have watched the second week videos. In there, uh, we can see how the normals, I mean, the distance between centroid and sides are calculated. All such places we are taking the normal vectors and also the angles we have to find out. So in most like uh, comparatively easy method, rather comparing the sides, I mean this uh, equilaterals, comparing with the regular equilaterals, the better method is to go for check for the equiangular comparison. So the skewness angle can be defined as 1 minus maximum of 90 degree minus 90 or 180, 90 minus alpha I by 90 degree. So the skewness skew angle here we can find out. So here this one is the angle, the diagonals, angle made by the diagonals. that is angle alpha. So the skew angle becomes 1 minus maximum of 90 minus alpha by 90. So if uh, this one uh, we have to reduce actually. So in these two methods we can find skewness. Next one is orthogonality, mesh orthogonality. So mesh orthogonality is somewhat similar to skewness. Some in some um, supplements you might they might have interchanged these as well, but mesh orthogonality is between two normals actually. So it is how we have already discussed how in control volume, I mean finite volume method, the phase and the flux through the phase is important. So in that terms, is mesh orthogonality or non-orthogonality. That becomes important. Suppose this red arrow represents the outward normal vector of this uh, face, this common face, and the, black line represents the vector connecting two cell centers or centroids. So, what is the angle made by this uh, outward normal vector to the uh, vectors connecting the centroids? That is the orthogonal angle, orthogonality angle. Not sorry, non-orthogonal angle. So this uh, value we have to find out. It is this if you see this element is skewed element. So uh, the results the results can distort if the value of this non-orthogonal angle go beyond 70. So 65 to 70 is somewhat workable range. Beyond that, we will uh, uh, consider it as highly non-orthogonal. So in such cases, uh, our computational process becomes complicated, and also errors can creep in the computation. Next one is mesh smoothness or growth factor or expansion factor. So how smooth is the transition? By the word smoothness itself, uh, you can understand how or what it means actually. So this smoothness is how smooth the transition happens. So in a cell, I mean in a when we are meshing a domain, there will be different cells having different uh, sizes. I mean there will be small cells, medium size, large size, everything, because to fill that particular shape, there will be different sized cells. Uh, uh, how these small cells are growing to larger cells. That is something called smoothness. So here I have seen two things. One is uh, the first one is steep transition, second one is smooth transition. Here, if you see this heights for the first four layers is almost similar. If I am calling it as delta y, then the delta y for this height, if I am taking for one particular cell as delta y, then delta y for all the four layers is same. But suddenly after that, it abruptly changes to some higher value. So first four layers is having one particular value, then the other two is having entirely different values. So this is something called a steep transition. So suppose if for a uh, uh, flow over a flat plate, suppose this flat plate is a flat plate maintained at very high temperature. So some uh, fluid, some air is conducted over this uh, uh, flowing over this hot plate. Then there will be convection kind of layer of conduction, and then convection into the heat transfer into the airstream, free airstream. So suppose we all know how the velocity graphs will be. This right. Okay, so it switches to u infinity or the free stream velocity from this transition should be smooth. To capture this transition, if we are using uh, this kind of steep transition cell, then it will be like this is the flat plate. So this first final layers will be very gradual. Then it will be a sudden straight line or something. So it will be sorry. So, so it will be go like this and this and suddenly a straight line, because these small cells, this first layer of cells, these values we can will be having small increments, small changes we can pick up. But once this sudden transition, sudden steep transition happens, it directly get a straight line or some jerk will happen. So to avoid that, there should be some smooth transition. So if you see the first layer is having delta y1, the next one is having somewhat higher, but not too large, but somewhat a small increment to the delta y1. So delta y2 is somewhat larger, but not too large. So this is gradually increasing in height. So such kind of transitions are called smooth transitions. So this smooth transition is called smoothness or expansion rate, or by which of its activity it is called growth factor. So in such cases, uh, if we are plotting the curve, it will almost capture our variation velocity. So for a case, uh, for an ideal case, it is said that should keep 20 percentage growth rate. Uh, Delta y2 should be uh, uh, almost equal to the increment, the change, percentage change in delta y2 is should be 20 percentage more than delta y1, or in simply we can write as delta y2 by delta y1 should be less than or equal to 1.2. So this is somewhat an ideal condition. So we have to keep this kind of growth rates. But here you would be seeing like this is only for a two-dimensional thing. So this thing applies for 3D as well as. Also in if we are using some triangle elements here also, suppose we are using some small triangles. So this is a larger one, this smaller one. This transition should be in this transition should be smooth. So this I have what I have drawn is triangular discretization. So this is a larger triangle. These are small triangles, but this layer should grow in a fashion that we can capture the variation, and also it should be smooth. There should be sudden abrupt change or jerks. Okay, that is mesh smoothness. Okay, next one. Which type of next question? which type of mesh is best suited for complex geometries with curved surfaces. So we have already discussed similar question before. We have always said that structured mesh is uh, well suited for simple geometries. So we can eliminate that one. So other two is thing is uh, we have left with this unstructured mesh and hybrid mesh. Actually, these two can be easily these both of them suits for uh, complex geometries with curved surface. But the thing is, depends. If some portion of the okay, we'll come to that. So among them also, if we are considering the meshing effort for meshing, then the answer is unstructured mesh. So unstructured mesh can be used for any complex geometries because we will be having a large flexibility. But actually, that flexibility comes with a computational cost. Actually, when the when we have to fit an unstructured mesh to a complex domain, then the meshing process itself is the algorithms. We will be needing some robust algorithms for that. Actually, process is simple, but we have to find proper algorithms to fit a structured mesh. Hybrid mesh can also be used. Hybrid mesh is you can uh, guess that's a uh, combination of structured and unstructured mesh. We will so let us discuss what are structured and unstructured meshes. So simply saying, structured meshes are meshes that can be mapped to Cartesian, I mean coordinate systems. That can be the when if the grid points or nodes of the cells can be sorry, if the grid points of the cells can be uh, mapped to some coordinate systems, coordinate axis of coordinate systems, then it is called a structured mesh. So here different types of meshes have been shown. These all these are structured mesh. Here we can see this is a Cartesian structured mesh. It's a Cartesian structured mesh with the orthogonal faces. So here if you see the angles will be 90 degree. It's an orthogonal mesh, orthogonal structured mesh. Also you can see here the inflation layers, that is expansion layers have been given. The lower layers are having uh, small thickness and it is gradually increasing upwards. So if you see here, you can see it's actually this portion is similar to that of the Cartesian mesh, but to accommodate this curve, here some portion is angles are not actually orthogonal. Angles are varying, just some skewness is there. There is non-orthogonal, but still structured mesh. Also, we can create curvilinear or body fitted structured mesh. Here, if you see the central point, this is an aerofoil thing. The mesh around this is still a structured mesh, but it's a curvilinear structured mesh. So this uh, mesh will be following polar coordinate system or something. If that kind of system. Here, if you see, still you can see this the elements are orthogonal. Or suppose we are taking circular, I mean, flow through fully diluted flow through a circular cross section pipe or something. There also we can take polar coordinate systems. So that is much easier to map than Cartesian systems. So these the types of meshes where the nodes can be easily uh, mapped to a coordinate axis of coordinate systems, selected coordinate system, then it is called structured mesh. Let's see what's an unstructured mesh. So in unstructured mesh, uh, the mesh won't be having uh, the elements or the nodes cannot be mapped to easily mapped to any coordinate system, and it is best suited to accommodate complicated or complex geometries. So if you see here, this hemicyclar plane, almost all the elements are quadrilateral, not squares. You can't see any squares or rectangles here. Almost all the elements are quadrilateral elements. This is on typical unstructured mesh. It's a 2D case. Here, if you see, it's a tetrahedral elements. This full domain is meshed with tetrahedral elements. Uh, uh, if it was a 2D, then we would the unstructured counterpart will become the triangular. Here it's a polygonal mesh or polyhedral. When it's come to 3D, the shape will be polyhedral. So this is actually good for if you are meshing for some uh, internal flow through pipes or something. The best suited mesh will be polygonal mesh because of the volume capturing. So that's what unstructured mesh is. Then hybrid mesh. By the name itself, you can know it is a combination of structured and unstructured mesh. So here, if you see in this layers, some particular layers have been meshed with uh, hexagonal cells or brick shaped cells. Then beyond that, some part is meshed with tetrahedral cells. So this combination, like if we are using combinations of meshes, structured, unstructured, or different types of cells, different types of structured or different types of unstructured, or such case becomes hybrid meshes. So here is a hybrid tetrahedral mesh. Here, if you see it's actually flow over a wing of an aeroplane. If you see the air domain or the fluid domain is meshed with tetrahedral mesh. Also, the wing is meshed with tet elements, but the layers, boundary layer or the immediate layers have been given some prism layers, flat layers to capture the discretion or something. The region of interest. When we are more interested in this area, we'll try to give more structured mesh there. Similarly, here the polyhedral mesh is given for the fluid domain as well as the wing domain, but the interfacial region is meshed with a structured mesh. So, such kind of combinations are called hybrid meshing. Any doubts? So, next question is, what is the key difference between explicit and implicit boundary conditions in CFD simulations? So, can you tell what is the answer? Explicit conditions specify values directly at the boundary. Implicit conditions involve solving additional equations. Explicit conditions are more accurate, while implicits are faster. And the explicit conditions require special meshing near boundary. Can you answer? So, simply saying, do you know what is explicit and implicit boundary conditions? Actually, it's in the name. It's the name itself gives away the content. Explicit meaning explicitly expressing. We are specifically specifying what is happening at the boundary. So it is actually another name for Dirichlet boundary condition. So implicit is other type of boundary conditions. So explicit meaning direct, or we are given explicitly giving values at the boundary. So Dirichlet boundary conditions are known as explicit boundary conditions. So the answer is one, which is we are giving a particular value, or we are giving constant values to the boundary conditions. So boundary, we are giving the values of pressure, temperature, anything, whatever is the parameter we are studying, that we are giving some values there. So again, implicit boundary condition. One of the implicit boundary condition is Newman boundary condition that I said. Suppose if it is insulated, then the equation becomes dou T by dou X is equal to 0. That's the insulation equation. Then we will have to again discretize this boundary condition. This boundary condition we have to discretize, and some elements we will be added there. Some elements we will be adding to what uh, inside the source state. So this is true in terms of implicit boundary conditions today,
Uh,
for today.
yeah. Just I wanted to may raise a request. Am I audible to you?
Yes, yes.
Yeah. Just I wanted to raise a request that last session happened from 5 o'clock. Actually, I'm working over here with industry in Bharat Forge, so it will be helpful if the session can actually take place after 6 or 7. I mean, at this time, if at 7 or 7:30.
No, actually, there are we are doing parallel. The other session is like Saturday 3 to 5. That's what you're saying, no?
No, no, that's why I'm telling Saturday is working of mine. So
Yeah,
if
yeah,
I'm just requesting
yeah. I understood. But the
if
thing
it can happen.
is, but, we are doing the sessions parallelly. Actually, you only need to attend either one, because we will be, both of you will be
Okay,
helping the learners with the assignments. Weekly
okay,
assignments
okay,
will
okay,
be having.
okay, okay.
So you need to
And
attend anyone.
okay, and I just wanted to ask one more thing, sir, Manjunath sir.
Yes.
Sir, in the prerequisites of the course, because my area has been mechanical, mathematical modeling in means related to some means finite element method, means on I have done in the continuum mechanics based on mechanical modeling, not not thermal and heat transfer wala part, CFD wala part. So,
Okay.
hello,
Yes. Yes. I'm
can you
hearing.
hear me?
Yeah, I'm hearing.
And in the course outline, it's mentioned that I haven't been into that programming stuff. I means it is the prerequisite of the course that there should be one programming language should be there which you should know, and pertaining to that numerical method. So means how intense the concept will be used in the upcoming lectures. Can you please tell me?
Uh, that actually I need to check, because I am also I have seen up to uh, when I have to see the other questions, because you won't be having much intense, because uh, once
Hmm.
you have know the methodology, CFD methodology, you will be knowing that uh, we have a geometry, we are discretizing it, we will be getting with some
Yeah.
algebraic equation. That algebraic equation we have to solve. So this
Yeah.
solving this algebraic equation cannot be done manually actually. When we have this number of, when
Yeah.
we have to reach some certain level of accuracy, we have to iterate it for
Hmm.
n number of times. So it is
Yeah.
best to know. Suppose you are given some with some problems you want to work out, because going forward the faculty will be showing in Excel or some
Yeah.
softwares or something. He will be showing this
No,
can be done like.
Excel is okay.
Yeah,
Excel is okay,
Excel
but
up to third
uh,
week, what is listed in third week, this Excel are showing. But still, when
yeah.
moving forward, when you are given, suppose we have a rectangle domain, so we
Yeah.
have to discretize it somehow. suppose 50 by 50,
Yeah.
we have to discretize,
Yeah.
and then you will be, you can imagine how much, if 50 by 50 is there, then 2500 cell will be there.
Yeah.
Yeah, so then we'll have to uh, find,
Then
I
sir
mean,
will be using MATLAB for that, or Python. What he will be using?
you can use, because all these thing is iterative solution. We Either we will be using
Yeah.
Gauss-Seidel method, TDMA you will be knowing tridiagonal matrix algorithm. Everything
Yeah.
that will be there. You can use anything if you are knowing C, C++, MATLAB, Python, anything that is comfortable that you can learn. You can learn to do that,
Hmm.
because once
Okay.
you don't know the uh, I mean, coding or something, you won't be knowing how we are calculating, because the meshing and solving this algebraic equation is done separately. First, we will be meshing the
Yeah.
geometry, taking the geometric parameters from the suppose like delta x, delta y, all those things. These geometric
Yeah.
parameters we are taking from the geometry after meshing, and we are
Yeah.
plugging it in the discretized equations. Then we are converting it into
Yeah.
algebraic equation, then solution of algebraic equation.
Yeah.
So this solution of algebraic equation is
Yeah.
done entirely separately. So after solving,
Okay. So
we are mapping it back.
no, no. Oh,
So
I'm just asking ki that solution part will require programming skills, right?
yes, it is not that you
So
have
will
to.
that
The basic programming is doable actually.
okay? So no, so we will be given with the straight away problems, or will there be a session on programming fundamentals of it at least to get us acquainted with the syntax and all for doing it, or should we means I'm just asking you out of concern, or should I start means parallel course with the some programming language?
I will suggest you to start with some program, because there is no programming
Okay.
side help from this our side.
Okay.
We won't be going deep into any programming language. We will be strictly
Okay.
sticking on to methodology, how we can uh, establish this particular
Okay.
following method into language. So
Okay.
in
Okay. Okay. I just
okay, in MATLAB it will be doing in one method. There will be some small differences, because all the
yeah.
programming language at the back end is working similarly. So it will only be
Okay.
difference in the syntaxes and all.
Okay. Thank you. Thank you,
Okay,
sir.
thank you.
Thank you.